Under protein synthesis, we're really far in this unit, so you might have to click the little button that says show more. I would like for you to go to Mutations, Sickle Cell. My cursor is on it. Mutations, Sickle Cell. You might have to click the little view more because we're pretty far in the unit.
Mutation sickle cell?
Mutations, Sickle Cell. My cursor's on it for you.
Oh, I didn't have to. Oh, yeah.
It looks just like this.
Do you need help, Carly? No, I found it. Are you sure about that? Yeah. Okay. Thanks.
Did you find it, Luke?
All right. Oh, God.
How is it over there, Ferris? You find it?
Yeah.
Okay, thanks. I can't see over there. All right, so please look at the background. I'm at the top where it says black background in blue. Look there. I'm going to read it to you today. It says, sickle cell anemia is a serious condition in which the red blood cells can become sickle-shaped, that is, shaped like a seed. Normal red blood cells are smooth and round like a donut without a hole. They move easily through blood vessels to carry oxygen to all parts of the body. Sickle-shaped cells cannot move easily through the blood. They're stiff and sticky and tend to form clumps and get stuck in blood vessels. The clumps of sickle cell block blood flow in the blood vessels that lead to the limbs and organs. Blocked blood vessels can cause pain, serious infections, and organ damage. Hold on just a second, please. Raise your hand if you know anyone that has sickle cell anemia. Okay. Sickle cell anemia is our real-world example of one change in transcription and translation. One DNA nitrogen base is different in the segment of DNA that codes for the protein to make your red blood cells in a person that has sickle cell anemia than the person who doesn't. So you're going to discover that mutation today and what happens. Would you please look at my screen? Those are your red blood cells. They look like donuts without a hole. They look like the tubes you ride on behind a ski boat sometimes. They carry oxygen for you. This is an image from a microscope of sickle cell anemia. This individual has some cells that are like normal, quote, red blood cells, and then some that are sickle shaped. Red blood cells are red in color naturally. That's because they're made up of mostly iron, and iron, like rust, if you've seen rust, has an orange-red color. The sickle cell red blood cells don't do the things well that you just heard me read. They don't carry oxygen well, they get stuck in blood vessels, and they can cause some problems. You're about to explore how this happens. Nina, yes?
So it creates blood clots?
Yes, it can, yep. So you will need your table for the second half of this, so just as a heads up. Let's look at what you're gonna do. I actually want you to jump all the way to number 4. Thank you for getting there. I have given you the DNA segment that codes for red blood cell protein. Your task is to first tell me what the complementary sequence on DNA would be. So the first row is DNA. Please listen before I go on. The second row is what mRNA would be made from the DNA strand you just made. And number 6 is what would be the amino acid sequence. So if we don't have sickle cell anemia, you just did the strand, the DNA strand for your red blood cells. And then you coded, you transcribed and translated out to the amino acid sequence. Then it tells you where the mutation is for people who have sickle cell anemia. I highlighted it yellow on your document, or on mine. I'm actually not sure if it got on yours before I uploaded it to Google Classroom. It wants you then to write the new mRNA and the new amino acid sequence, so you can see the effect of one nitrogen base difference. What questions do you have for me right now? I I do want you to tackle this one to start by yourself. And let me know how I can help you. Go ahead. Check in with our virgin students.
Miss Olson, should we start at number 4 or?
Yes, please, start at number 4. Thanks for clarifying that for us.